All right, so we have, I think, a bit of an ambitious agenda for the next several lectures. We want to teach you guys a bunch of things, and we're going to try to do it all in 6 lectures. So we're going to, I'm going to today go through a very just kind of brief, superficial connection between what you saw in Minimax, the Minimax lecture, to an analogy and convex optimization. I'd like to go through in detail. The notes aren't really that superficial, but we don't really have time to go through the connections in that much detail. Of course, you can come and ask me questions if you're interested. Then I'm going to teach you guys about duality and the KKT conditions, which are two concepts from optimization that I intended to get through when we went to norm optimization several units ago, but we didn't have time for it. And I think of these as, well, really one and the same. That's how I do them, is that duality and the KKT conditions are intimately linked. But more than that, they provide just an essential tool for understanding problems that arise in tons of contexts in statistics and machine learning. So then after that, I'm going to show you how we can use this notion of duality and KKT conditions to prove a bunch of stuff in a specific setting, and that setting is going to be sparse estimation. So we're going to go through in a lecture, maybe a little bit more, a bunch of theoretical results that use duality and KKT conditions, and then we finish up with some other stuff. But that's the agenda in the near future. Okay, so here's we're going to, like I said, just kind of briefly touch on the connections between minimax rates in statistics and optimal rates of convergence in optimization. So there's kind of an interesting connection here. And so in statistics, right, we have this notion of minimax lower bounds, and they look kind of something like this. I'm going to write them in, this is in a really informal way. The min over all estimators of the max over all parameters okay, and so Larry taught that kind of like, he saw this as a distribution actually, but often I can parameterize distribution by the parameter, so that's why I'm going to write the max overall parameters. You can think of this as, this could be infinite dimensional too, it could be a function, so it's not necessarily just in the parametric case. Of the expected loss between my estimator and the truth, and the truth is like the parameter. So if we want to think about the non-parametric regression case, right, don't confuse this with meaning a parametric model. This just means an object of interest that we're estimating. So the parameter is the function, and so I'll take a max overall, maybe say underlying regression functions that have one derivative, and whose derivative is Lipschitz or something, with Lipschitz constant L. That might be this maximization. I take a min over all estimators of that regression function. So I can get that from any kind of non-parametric regression technique I want. And then I look at the expected loss between that estimated function and the true function, and I can measure that like an integrated squared loss or something. So this could be pointwise. I could be asking for the square difference at some point or something. All right, so that's the object. This is the framework of interest in minimax theory. And why do we study this? Well, I mean, I'm just kind of repeating what you already know, but I'll just say it for completeness. One is that it gives us an understanding of kind of the limits of our estimation capabilities. And so overall, this tells us how good can we do. If I look at various things like the dimension of the problem, maybe something to do with the smoothness of the function, it gives us an understanding of the limits of our ability to estimate whatever this parameter is. The other is that we like to try to match it with the rate attained by a particular estimator. And so if we know that, for Lipschitz functions, kernel smoothing has the minimax rate, then up to rate, there's not really any point in finding in trying to seek another estimator. Right? It's comforting to know that, well, we're justified in using kernel regression for Lipschitz functions, or for smooth functions whose derivative is Lipschitz. So how about optimization? That's it's a related concept, and so it's interesting to see this pop up. We talked about optimal rates of convergence optimization, and they don't write it like this, but I'm going to write it like this just so that we can compare it. Let's suppose I'm trying to minimize a function f. Okay, so I'm going to look at the min over all algorithms that I'm using to, these are optimization algorithms used to minimize that function. Over the max over all function, choices of function that I'm looking to optimize or to minimize. And something like the algorithms guess at the kth iteration. So maybe this is the algorithm's guess for the optimal value of the function, the minimum value of the function, minus the true optimal function value. Okay, so let me just make a couple really coarse comparisons. Estimator here is like an algorithm, right? That's what's on the outside the min. So we can choose how to estimate a parameter in statistics. We can also choose how to optimize a function optimization. This is up to us. So if we can derive the lower bound, and we can also find an algorithm that achieves that lower bound, then we're satisfied. Just like here, if we find an estimator that achieves the minimax lower bound statistical rate, we're satisfied. So the underlying parameter here is like the function we're looking to minimize. Okay, that's the analogy. There are lots of important differences though. Oh, sorry, one more quick analogy. K here is like n. It's like the sample size. So this minimax rate is going to be in terms of n. We're going to see something like, say, n to the minus 1/3. If I'm talking about functions of bounded variation or Lipschitz, something like that. The rates are going to be in terms of k. Okay, it's like if I allow myself more iterations, I know I can do better. Just like if I allow myself more samples, I know I can do better. So what are some important differences? Well, one is that here there's nothing random. There's no expectation in this bottom one. So you'll see that actually, when we prove how to construct this lower bound, we don't have to be kind of as sophisticated in some sense as we do in constructing lower bounds in statistics, because there's nothing random. We just need to find one really hard example. And we'll see, you'll see two kind of concrete examples of that. So we have to find one really hard function to optimize. If we can do that, we actually have the minimax lower. The other important difference is that, remember we said that, well, in minimax theory and statistics, there's no restriction over estimators here. This could be like an estimator that requires, an enormous amount of computational time. It doesn't have to be a polynomial time estimator. We generically don't make these kind of restrictions. This is just happening now in the last, maybe say, year, that people are looking into minimax rates under computational constraints. Whereas here, we actually always restrict the function, the algorithm class. It doesn't make sense otherwise. So optimization people have been doing it right for a while. We do restrict the analogy of the estimator optimization. We only look at algorithms that kind of have access to a certain amount of information. Otherwise, it wouldn't make sense. And so in both, in the inner ones, we always restrict in both settings as well. Right? We look at some parameter space or some function space. Okay, and so there are versions of optimal rates for optimization where we do actually have some kind of random noise model. Like we don't observe the function, we observe a noisy realization of it, so then there would be some kind of randomness here. So it does get more sophisticated, but at least this is like the very high level comparison. And I'm going to give you two concrete examples. We're not going to prove either of them just for time, but the proofs in the notes for both of the examples I'm going to give you. And I should also mention that in the advanced optimization class, I was told that coincidentally, they're covering lower bounds this week. So that's pretty fortuitous. You can just go sit in that class. I think it's right after this class, is that right? So you'll get a lot more detail from that class. Okay, so let me just tell you two results. I'm going to state them, and we're not going to prove them, but I'll give you an idea of how they're proved, and we'll just move on to duality. So the first thing I want to do is look at non-smooth first-order methods. So this means that I'm going to be looking in a situation where I want to minimize a function, f, unconstrained. So there's no, I want to minimize f of x over all x. This is an optimization problem. F is going to be convex. But that's it. Well, we'll actually place another restriction on in a second, but importantly, it's not smooth. Okay, so it's a convex function that's not necessarily smooth. And what I mean by a first-order method, and again I'll make that precise in a second, is just I'm allowed to look at subgradients of f to minimize it. That's all I'm really allowed to look at. It doesn't have gradients necessarily because it's not smooth, but it has subgradients because it's convex. And to minimize it, I can look at its subgradients. So what's the canonical method that we know about? Well, we talked about this before. I can use the subgradient method. Here's an example of an algorithm that's used to solve this problem. And what do? Well, I just start off with a guess. I guess I call it y0 on the notes. Some initial guess y0. And then I take, I just repeatedly take a step in the direction of a negative subgradient of the function at my current point. Okay, so I first, we're gk, right here, gk minus 1 is a subgradient of the function at the point yk minus 1. Repeatedly move in the direction of the negative subgradient. And this is a step size controls how far we go in the direction of that negative, of that subgradient. And because it's not a descent method, remember, I'm not guaranteed to decrease the criterion in every iteration. I actually keep track of a second list of numbers, and that's why I call this yk, just so that I can distinguish that what we actually use as the estimates are the second, the iterates, and that's just, I just look at the history from step 0 to step k, and I take the guy that has the lowest value of the function. Okay, that's it. So that's the subgradient method. And we have some rules for choosing tk, and we have some convergence results on the subgradient method. And I talked about that last time. Just to remind you, the main conclusion that we have is that if f is convex in Lipschitz, so if the function that we're trying to minimize is not only convex but it's Lipschitz, and I choose the step sizes appropriately, and after k steps, I have the following bound. So the function value at my iterate, my k iterate sk, minus this is the optimal function value. This is the minimum of f over all x. The point is f star. It's bounded by constant over the square root of k. Okay, where this constant depends on where we started, x0, and also on L, which is the Lipschitz constant of the function. Okay, so the question we're asking now is, can we do better? Right, is there some method that can minimize the function faster than 1 over the square root of k if the function is convex and Lipschitz? Okay, so that's not terribly well defined. In the sense that we have to make a concrete statement, at least in this course, in a short enough space that I can put in the notes, we have to put a restriction on what kind of algorithms we're willing to look at, how these sequences of points are generated. So we're going to ask, can we do better with what we call a non-smooth first-order method? And what I mean by that is that I'm going to allow myself to look at any algorithm that has the following property. Its updates, xk, are in the span of some initial guess. Yeah, some initial guess, plus the span of subgradients that it visits along the way. Okay, I can take any point that's where I started off with, and a linear combination of the subgradients I've seen up until now. That's what we're going to call a non-smooth first order. So the way that it chooses a point in this set can be very complicated. Right here it's pretty simple. If we take a step in the direction of the latest subgradient, we actually know just inductively kind of right that this is the span of the subgradients that we're seeing, because if this was in the span of the subgradients up until k minus 2, then I'm just taking a step in the k minus first subgradient, so definitely isn't in the span. And then I'm just choosing kind of greedily to be the point that has the best function value. But I'm going to consider any algorithm that is allowed to make updates like this. Could be excruciatingly complicated, but all I know is that at any step, this is its restriction. And the interesting answer, and actually the encouraging answer, which is proved by Nesterov, and I should have mentioned that everything we're talking about today comes from Nesterov, at least from the optimal lower bound. And he's a pretty dominating figure in this field, and I also gave some references to his book for more information you can look at. The answer is no. So we can't do better. So in other words, if all you know is that you have a convex function that's Lipschitz, pretty broad, and you're allowed to use subgradients and take linear combinations of subgradients, you cannot do better than subgradients. That's pretty encouraging because it's actually it's a very simple method. In some sense, we think of it as really slow. We always criticize it for being so slow. But this tells us that if all we're allowed to do is look at subgradients, you can't do any better. Okay, so what's another result that I want to mention before I talk about how we would prove these? It's the smooth first order method case. Okay, so same setting, except for I'm going to assume that f is convex and differentiable. And what do we do? Well, let's look at the canonical method for this. We already learned it. So it's gradient descent. And we choose some initial x0, and then we're going to take xk to be xk minus 1 minus the step size tk, and then here we're allowed to use the gradient, right, because it's smooth. So I take the gradient at xk minus 1 and I move in that direction. Okay, and so what do we know about gradient descent? We know that if the function is convex and differentiable, and if additionally its gradient is Lipschitz, then we have the following convergence result. And so we didn't prove either this one or the one for subgradient method, but the proofs are very straightforward. They don't involve fancy math. They're just not things you would necessarily think of in the first place. And so those proofs, they are in the notes. So the proofs of the upper bounds as well as the lower bounds for all this stuff is all in the notes in case you're curious. We know that f at the kth iterative minus f star is no more than, now we get c over k. Okay, so the difference is an order of magnitude. We get root k versus k. Again, this might just look to you like at this point mathematical bounds, but it actually makes a big difference in practice. We flip this around and we ask how many iterations do I need to get an accuracy of epsilon? That's like another way of thinking about these bounds. I need about epsilon iterations here. Oh, sorry, 1 over epsilon iterations. That's how it scales. You can accuracy of epsilon. This tells me I need about 1 over epsilon squared iterations to get an accuracy of epsilon. So if I'm running gradients on a smooth problem and I want to go from, say epsilon equals 10 to the minus 3, 10 to the minus 4, I basically just need 10 times more iterations, right? That's all I need. But here, I need something like that squared at many more iterations, right? So to go to 10 to the minus 4, I need like 10 to the 8th, which is like 10 million iterations. Okay, so it makes a very big difference when you talk about the accuracy, the number of iterations you need to achieve a certain level of accuracy. And so we are asking the same problem, can we do better? That's the interest in lower bound. So we're going to have to restrict the problem class again, the algorithm class again. And so we're going to say, can we do better with a smooth first order method? And so this is any method that performs updates. It's really just the same as up there, except for I replace subgradients with gradients. So I'm allowed to look at any method that produces iterates that satisfy they're in the span of some initial point plus all the gradients I've seen so far. So this might be surprising to you if you haven't seen this kind of stuff before, but the answer is actually yes. So the gradient descent is not optimal. There's actually something that has, what we can prove, let's start off one step at a time. What we can prove is that the lower bound for estimation in this setting is actually 1 over k squared. So if I use the first order method on a function that's convex, differentiable, and its gradient is Lipschitz, then the lower bound we can construct is 1 over k squared. Now just like Larry mentioned for the statistical minimax rates, at that point we don't know whether or not our lower bound construction is too loose or whether we have some kind of suboptimal bound here. Or whether there's some other estimator that has a better way to least level bound. We don't know. But Nesterov, in some pretty classic work, he proves that both the lower bound is 1 over k squared, and there's a very simple twist, a variant of gradient descent that I can run, that achieves that rate. That achieves the rate 1 over k squared. So actually now this does settle the issue that it's not optimal. The optimal rate is 1 over k squared. And we can apply something called acceleration to get it down to that rate. And I put the method in the notes. You can write on the board. It's a very simple twist on gradient descent. But it can work a lot better in some problems. And in terms of rate, it's also a lot better. Okay, so for the sake of time, I'm not going to prove either of these. But I'm going to tell you how they're proved. And in both cases, you can notice that if I want to prove something like the minimum overall, say, first order methods of the maximum overall functions that are, say, differentiable and whose gradient is Lipschitz, that the difference in criterion by the kth iteration is bounded below by something, I can always say that this is bigger than or equal to the minimum over all algorithms of how will they do on just one particular function. Let me pick some function. I'll call it f of xk minus f star. Right, certainly if I take the maximum over all functions, it can only get bigger. So this is lower bounded by how well they do on just any one instance. Now, if I find an instance, a particular function that's just really, really hard for this algorithm class, then I'm done. So that sounds kind of simple, right, compared to the way we constructed lower bounds for statistical problems. But it actually involves some amount of cleverness, as you might imagine, in picking this function. So there are two very clever choice of functions that are very hard for either smooth first-order methods or non-smooth first-order methods. And they're in the notes. And they're not particularly insightful when you look at the function, but their construction is such that you can prove that essentially any, let's say any first-order method, as it tries to minimize this problem, the way that it constructs the gradients is such that, for example, at the kth step, its iter has to have zeros in every component k plus 1 through n, if the problem size is a dimension. And if the solution is something that's maybe supported fully on all components, then you can have a lower bound from how far away any iter is that uses these gradient updates from the solution. And that's actually the basic proof structure for both the non-smooth and the smooth case. Okay, are there any questions about kind of high-level overview? I realize it's kind of fast and not too detailed, but I wanted to give a flavor of the relationship results. Yeah.
In the subunion, that we mentioned that we are not sure if we are performing a descent. Why is that?
Well, I mean, the fact is that if I take a subgradient of a function and I look at function values, if I move in that direction, it's not necessarily a descent direction. So there may not even exist a scalar multiple that brings me in a direction where I make the function criterion value smaller. You can show that's true with gradient descent. Like you can prove that's true if the function is like Lipschitz. If the gradient is Lipschitz and has a certain constant, then we can upper bound the function by a quadratic. And we can prove explicitly that if the step size is small enough, and I move in the direction of the gradient, then that quadratic decreases, and therefore the function does too. That's like a very simple way to say the gradient descent is descent method. But for subgradient descent, we don't have that same construction. You can just take examples in practice where if I take steps in the direction of subgradients, I can actually make the function larger. So I don't think it's actually a huge deal. It's not something people worry about. We just keep track of the best function value. And I should mention, actually, thanks for bringing that up, the accelerated gradient descent method that Nesterov proposes to achieve the optimal lower bound, the rate of convergence, is itself not a descent method. It also can make the function larger. So we do the same trick where we keep track of the function value of each iteration. Let me write the acceleration on the board so you can at least see the punchline. So here is n optimal achieves the optimal lower bound. First order method for that function class. Differentiable convex functions whose gradient is Lipschitz. And the story actually gets even more rich because it turns out we can achieve that rate not only for a smooth minimization problem, but also for certain types of non-smooth minimization problems. If we do what's called a composite minimization problem with certain assumptions, we can still achieve the rate 1 over k squared. So there's a lot more that can be said, but I'm just going to stick with this stuff. So acceleration works as follows. Accelerated gradient descent. So who else could it be due to other than Nesterov? But here's what we do. So we choose some initial point. x0. And then repeat the following steps. I'm actually going to take a gradient descent step, not at xk minus 1, but at a different point y. And how do I get that point y? Well, I'm going to take where I was, and then I'm going to add a term that is often called a momentum term, and it pushes me in the direction of where I was going. Okay, I'll draw a picture in a second, so you might understand better, but I look at where I was going from step k minus 2 to step k minus 1, and I take that vector, and I add some multiple that vector to the current area. So it gives me momentum to keep going in the direction that I had been traveling from step k minus 1 to step k minus 2 to step k minus 1. And then I take a gradient descent step at y. So then I just let xk to be equal to y minus tk times the gradient of f of y. Yeah, question?
Isn't that similar to just using a larger step size on the previous iteration?
Not quite. You'll see why in a second. So let me draw a picture. I think it's going to help clarify. So let's suppose I was here. So this is going to be xk minus 1, xk minus 2. And xk minus 1 now. And instead of taking a gradient descent step from here, I actually allow myself to be pushed in the direction of where I was going. But let's suppose that the minimum is here. Then I actually don't take a gradient descent step from xk minus 1, but I actually allow myself to be pushed in the direction that I had been traveling and take a gradient descent step from here. And this is y. And so intuitively, what is this doing? Well, the closer you get to optimal, the smaller the gradient. So the less it means to be taking a step in the direction, step size times the gradient, because the gradient is small. The gradient is 0 at the optimal point for a smooth convex function. So what this is doing is that it's actually pushing me farther towards the minimum, because it knows that as I get closer and closer, the gradient is going to be smaller. And if you look at this weight here, as iterations proceed, this gets closer and closer to 1. Right, so there's more and more kind of effective, the role of this momentum term is larger and larger as the iterations proceed. So the question was, isn't this the same as taking a step, the larger step size from the previous iterative? It's not, right, because I'm taking a gradient next step from here versus here. Those are actually two different points. The gradient's going to be different.
What I'm saying is, for the previous step that we took to be from x to go from xk minus 2 to y directly, and xk minus 1 would become y in this case. So this would be like taking a larger step towards this direction.
No, but I think the point is that okay, so that cannot be the only distinction, because then it would be a first order method, but I'm temporarily blanking on why that's not the case. I mean, this is a first order method, but I don't think it's the same as just taking a larger step size.
Do you evaluate the function at xk minus 1 rather than 1?
No, it's okay.
You mean for the iterate? Yeah, you evaluate at xk. Those are the iterates, that's right. Yeah, so it does seem like this has to be the direction of the gradient. So if I took a larger amount, let me think about that. I'm actually not. I'm not sure. The funny thing is, I was asked this question 2 years ago in optimization, and I remember thinking about it, and I had an explanation, and now I seem to forget it. But it's a tricky question, yeah.
Okay, another thing is, because we say this is the optimal one, is it always better to use this one, this algorithm? Or are there cases where it's better to use the simple gradient descent algorithm?
It usually doesn't hurt to use acceleration. You'll see that there's these characteristic Nesterov ripples, is what they tend to be called, that the function looks kind of like this as it's being minimized, whereas the gradient descent, if I plot the gap between the kth iterate and the solution, looks much more smooth. So this version of acceleration makes kind of like bursts of progress, and it can be non-monotone, so it can do this. That's why it can be not a descent method. But typically what you'll see is that it does not hurt to use acceleration. That's not always true, but it is generically true with smooth minimization problems. When we start talking about this method applied to a non-smooth minimization problem where we have like a composite structure, then it can be the case that using acceleration makes each iteration much more computationally expensive because of the way it's set up for those problems. And so it can be not worth it.
Okay.
That's the question. Yeah.
I think the difference between acceleration and larger step size is the momentum is not pushed from y, but from the previous x. So if you keep growing to xk, the next step, the next y will not be lined up with y and xk, but xk minus 1 and xk.
Yeah, but that's what.
Yeah, that sounds right, but can you say it one more time?
I mean, if you keep going the graph, then say we got to the point xk, then
Well, xk is going to be something, right?
yeah, if we are using larger step size, the next step is probably going to.
Yeah.
Probably it's going to be lined up with y and xk. But in acceleration, we are starting from xk minus 1, so the momentum is going from xk minus 1, not y.
Okay. Are you
Yeah. That makes sense.
Okay. Okay, yeah, question.
This is something very similar to what Anthony asked, but like in practice, is the momentum always k minus 2 over k plus 1? Like the weight for the momentum, or is it?
No, that's just one choice. So the convergence rate shows that if you have, I can stick in theta k here. And if I have any theta k that satisfies some summable conditions, then I get the 1 over k squared rate. This is one choice that satisfies those conditions.
So in practice, do you always make sure that theta k satisfies that, or like do you try to be more aggressive on this?
No, I think this is pretty standard in practice. Although I should say that there are many forms of acceleration. This is only one form of acceleration. I'm going to sound like I want to form a Nesterov fan club. I don't really. I'm just stating the facts. Nesterov has 3 versions of acceleration. And this, I think, is the one that we kind of typically employ the most. But there are versions of acceleration that use the entire history. So that use not only the difference between xk minus 1 and xk minus 2, but they actually here sum over the entire history. And then they use different weights. And they can be faster, but they're slower to compute. And there's one other one that is coupled with something called dual smoothing, which you won't learn. But there are more than one form of acceleration. This is the simplest. And when you use this, you typically always just use that k minus 2. All right, so that's a whirlwind overview of lower bounds and optimization. There's some pretty cool connections, I should say, to statistics, not only in the kind of superficial ones I pointed out, but also people have been starting to study things, again, recently in the last couple of years, like what if I don't want to minimize the function kind of an arbitrary level of accuracy, so that's C over K, but I'm going to allow myself to tolerate something like, I don't know, here I'll put like sigma squared. Suppose that's the noise level. Suppose I'm actually observing data from like a random sample. And this is I'm not giving any details here, but let's suppose that the noise level was sigma squared or sigma. And I told you that I wanted to find the solution not up until some arbitrary amount of accuracy, but only up until the level of noise that I believe existed in the data sample. That's reasonable because you might say statistically there's no reason to optimize past that. That's kind of something, in some sense, it's like irreducible, right? I think it's lower than sigma. Right? Then, if I allow myself to tolerate that, then actually these rates get really fast. And it's something that we see in practice, is that if you want a pretty good solution, so one that's up until the noise level, they don't look like 1 over k for smooth problems. A lot of smooth problems look like they're exponential. They look like they're actually more like c to the k for some c less than 1. There's a very cool interplay between statistics and optimization. And so people are starting to explore these connections now. And so these are, in some sense, pretty pessimistic because we're talking about, there's nothing random, and we're talking about optimizing up to an arbitrary level of accuracy. But the story is more optimistic when we consider a random flavor with allowing for error. Okay, this is a good enough time to take a break, and then we'll come back and do duality. As per my usual, I have a bad joke for you. This one is pretty bad. I actually thought of it earlier this afternoon, so you guys got to cut me some slack. So I can remember it. All right, so a non-convex function and its tangent line, we're getting into an argument. What did the tangent line say to the function? You think you're so much farther above me. Well, let me tell you something. You're not. All right, the punchline didn't work, but the concept is there. Put it that way. Okay, so duality is what we're going to study. So duality I think of as linked intimately to optimality conditions for optimization problems. And so it plays a pretty fundamental role. And we'll also see that in statistics and machine learning, I'm going to prove to you guys next lecture. And then at the end, give a couple lectures on Stein's lemma. I'm going to kind of bring it together, hopefully, where I show you how duality can come in and give us a crystal clear picture of a statistical problem that allows us to kind of read off the properties of the estimator. And so we have to learn duality first. And it's also, I think it's a very beautiful topic. And of course, everybody is of their own opinion. Here's the canonical framework for minimization problem, a constraint minimization problem. We're going to minimize a function subject to a bunch of inequality constraints and a bunch of equality constraints. And let's just remind ourselves, if we're doing convex optimization, this would have to be convex, F. These H's would have to be convex, and these L's would have to be affine, right? They have to be, like each one have to be like AJ transpose X plus B equals 0, or BJ equals 0. For now, actually, we're not going to assume convexity. That's one of the powerful and remarkable properties of duality, is that we can make statements, at least on paper, without assuming convexity. And then we'll see where convexity comes into play later. So we're just going to say we have an optimization problem. And it's of this form for some choice of functions. The other thing I would say as a heads up is that the arguments we make in duality theory and the KKT conditions to get kind of optimality conditions out and to derive the dual functions like that, they're all extremely simple. And it seems kind of like you're doing these little tricks. So I have oftentimes confused myself trying to remember them. They're very simple. So let's just see if we can get through them. So the first thing we do when we see this problem is we define what we call Lagrangian. Okay, the Lagrangian is a function, and it's a function of x, which is the optimization variable, but it's also a function of two other variables. We call them u and v. And u is an m-dimensional variable, and v is an r-dimensional variable. And I think about basically pairing each component of u with one of these inequality constraints, and each component of v with one of these equality constraints. Okay, and so the Lagrangian looks like a function plus the sum of ui times my inequality functions plus the sum of vj times my equality functions. That's the definition of Lagrangian. It's a function of three variables, x, u, and v. And we're going to define its domain. So the domain of the Lagrangian, we're saying it's only going to be defined for x, well, that are in the domain of the radical optimization problem. So whatever that, we'll just carry that over. Any v. And we're going to restrict u to be non-negative in every component. So this means that ui has to be bigger than or equal to 0 for all I. So its domain is whatever the domain of x was originally, non-negative u's in any v. Okay, so given that I construct that Lagrangian, it has the following amazing property. Well, actually, this is very straightforward, but it'll become amazing in a couple of steps. But it has the following property, which is that if I take any feasible point x, so what does that mean? Remember, that means that x satisfies those inequality and equality constraints. So it has the property that hi of x is less than or equal to 0, and Lj of x is equal to 0 for all I and j. And if I take any dual feasible u and v, okay, so we use the word dual for the first time. Don't be concerned, this is just terminology. I just mean, we just say that u and v are dual feasible if u is non-negative. That's it. That's all it means. It means that u, v are in the domain of the Lagrangian. We call them dual parameters. Again, at this point it's just terminology. So we take any feasible x and dual feasible u and v, so u that's non-negative, then I have the property that L of x u v lower bounds my function. Okay, that's actually not too hard to see. Why is that true? Well, look, if x was feasible, then first of all, Lj of x is going to be equal to 0 for all j, so that term's just going to be 0. The last term we don't worry about, it doesn't matter what Vj is, that's just 0. The middle term, we're going to have hi of x is less than or equal to 0 for all I. And ui, it was non-negative in every component. Right, that was my assumption. So it's just really trivial. That middle term is non-negative. I'm sorry, is non-positive. That middle term is less than or equal to 0. Right? So this is less than or equal to 0. If each ui was less than or equal, was bigger than or equal to 0, and each hi of x is bigger than or equal to 0. So I have this. All right, so pretty simple. In other words, if I look at the function L uv, so if I fix u and v to be dual feasible and look at the Lagrangian as a function of its first argument, this lower bounds f. Okay, I think I have a picture in the notes. Maybe I don't, but if you look at we can take examples. For example, we could actually construct a function, construct the Lagrangian and fix some u and v. You can see that the Lagrangian hugs the function below, everywhere. So it lower bounds f. It's a very simple construction that made this possible. So why did I like this? Well, it's because the next step, which is, let's define C to be the set of all x for which the constraints hold. So this is the primal feasible set. Okay, so I'm throwing around some words like primal and dual. Again, don't be concerned. I'm just going to start calling this problem up there the primal. You don't know what the dual is. You don't really know what the dual problem is yet, but I'll tell you what it is in a second, and you're going to see that the dual variables end up being, and the optimization problem end up being exactly these guys, u and v would call. So this is the set of all x that are primal feasible for that problem. Here's a very cool sequence of inequalities. If I take the optimal primal value, f star, right, so remember this is equal to the minimum over all feasible points, x and c of f of x, then because the Lagrangian lower bounds f, I can write that like this. It lower bounds f over all primal feasible points, right? That's what we just proved. L of x u v. This is true for any dual feasible u and v. So in other words, for any u that's just non-negative. Okay? Let me make one more step. This is actually bigger than or equal to what happens if I minimize the Lagrangian, but unconstrained, without the constraint that x has to be feasible. I'm just going to minimize the Lagrangian over all x. Call this L of x and v. I can only make that smaller, right? Because the minimization now is made broader over not just x and c, but any x. And I'm going to define this function, the minimum of the Lagrangian over all x, as just some function g, which is a function of u and v. I can always do that. I'm just defining the function g of v to be the minimum of all x of Lx. In other words, what we've proved is that for any 0 in any v, I have that the optimal primal value, I'll just call it f star, is bigger than or equal to GUV. I'm going to call this guy, this is a definition now, the dual function. And we often in optimization call that the Lagrange dual function just to differentiate it from other types of duals. Down to half-inch chalk here.
There's a whole box of it.
Okay. And I'll show you examples of how we explicitly compute that, but it is defined like this. So minimum Lagrangian over all x. And, okay, so this holds for every u and v, for which u is non-negative. So now let me actually do the following. Let me think about maximizing this lower bound over all u and v. Well, if that holds for any fixed u and v, where u is non-negative, then it's certainly true. It's certainly true that I maximize over all possible u and v. And so I still get the same inequality. And I'm going to call this guy now the dual problem. Or, again, I'll just sometimes specify that it comes from the Lagrangian, so I'll call it the Lagrange dual problem.
What are the other dual functions we have?
I mean, there's a bunch of other ones, like the wolf dual, for example, or I mean, another dual that we use sometimes that's a special case of the Lagrangian is like the Legendre dual, but it's usually this specific function. But I guess wolf is the other main one. Not sure. Okay. So what's the point of all this? Well, we started with the primal optimization problem, and through some manipulations that were actually really simple, we generated something we called its dual problem. So this is the dual problem corresponding to that problem. And it's defined by maximizing the Lagrange dual function, which we defined as take the Lagrangian, minimize it over all x, unconstrained. At the point uv, that's this function here, GUV. And so why do we do all this? Well, we get a couple of things out of it. The first thing I get is, well, this is useful sometimes. Let me call the optimal value of this dual problem, G star, just like I called the optimal value, the primal problem, F star. Well, I get this property called weak duality always. Right? We actually, that's just being shown right there. Truly proved. The optimal value of the dual problem is always less than or equal to the optimal value of the primal problem. Right? Because it's just constructed to be a lower bound. This is the best lower bound we can construct over all dual phi as the points. So it's going to still have that property. So that's useful sometimes because in some cases actually knowing a lower bound on the value of the primal problem or the problem you're trying to minimize is helpful in the context of the problem. And it could be the case that actually it's very difficult to obtain a solution or an approximate solution to that problem. But I can get a lower bound pretty cheaply from duality. I can construct a dual problem, maximize it, and I get a lower bound. But that's kind of less so the case. That's not really the reason why we like duality so much. The reason we like duality so much is that for a bunch of problems, we get something that we call strong duality. This always holds. This only holds for some problems. That's when G star is equal to F star. Which means that maximizing the dual problem gives the same value as minimizing the primal problem. Now, again, we typically don't only care about criterion values, we also care about solutions. When I write down a problem like that, I don't usually care about F star, I actually care about X star, the primal solution. And so, oftentimes in strong duality, what also happens is that we can compute what I'll call X star, it's the primal solution, or a primal solution, from dual solutions. U star, V star. So if I can form the dual problem, and I can solve it, then it gives me the primal solution. Now, it's not always the case that the dual problem is easier to solve than the primal, or that it's possible to even form it. But it gives us a second shot at solving the problem. A lot of times, and next time I'll go through quickly some of the major examples in which the primal problem has a structure that's difficult to deal with. The dual problem has a complementary structure. So if we can form it and solve it, we can get the primal solution without having to ever deal with it, with whatever the messy structure was in the primal that we couldn't deal with in the first place. Okay, so before we conclude today, I'll have a couple minutes left. I'm going to tell you two quick facts. The first is that this problem here, the Lagrange dual problem, this is always a convex optimization problem. In other words, the dual function itself is always concave. GUV is always concave as a function of UV. So I'm maximizing a concave function. We just call that convex optimization. Right? Because maximizing a concave function is equivalent to minimizing a convex function. That's true no matter what F was, H was, L was, it's always true. So it's kind of remarkable. The dual problem is always a convex optimization problem, no matter how messy the primal problem was. Now, so with the caveat, we can't always write down the dual problem analytically. If you give me the world's hardest non-convex problem, chances are I can't form the dual. But if I could, it would be concave, and the dual problem would be a convex optimization problem. Okay, it's pretty neat. Where did that come from? Again, it's a very simple argument. Let's look at this as a function of u and v. Right? So the dual function is what I get when I minimize this over all x. So I'm going to write that as maximize, or negative maximize the negative of this quantity. So I'm maximizing over x, minus f of x, minus this, minus that. As a function of x, what's this? I'm sorry, as a function of u and v inside, this is just an affine function, right? I'm maximizing a bunch of affine functions in u and v. I'm maximizing a ton of them, I'm maximizing over all x. When I maximize affine functions, I know that the maximum of any convex function is still convex. So that this thing is convex. So what we proved was that minus L was convex, and therefore L is convex. Okay, I went through that really quickly because we're essentially out of time, but look at the notes. It's always true that this is concave. Last point before we go is that when does strong duality hold? You can guess why we care about convex optimization so much. It's because essentially, if the primal problem is convex, then we get strong duality. That's true subject to like a really tiny qualifier we'll play next time. Basically, for any convex primal problem, we do get strong duality. So we get to enjoy all of this stuff here, like forming the dual, solving it, and then looking at primal solutions from the dual. Okay, that's it. I guess I'll see you guys on Wednesday.